thank you very much for your introduction. And now we switch from the qubit or from the pure quantum circuit to classical circuits, but they operate at the border to the quantum circuits. So our effort in this research is to build interface electronics with the potential to operate at very low temperatures. So maybe at the same stage or even on a monolithic chip together with the qubits. It's based on a collaboration between my company in Erfurt and Yokohama National University. So let's see, this is, okay. So just briefly, so CIS stands for Competence in Silicon. We develop sensors, and mostly silicon stands for semiconductor circuits, but we also do some superconducting circuits, and it's a private research organization. And I don't want to go into the details, but just showing that beside the superconducting quantum circuits, we also investigate diamond and NV centers in diamond. And recently we finished our first prototype of a magnetic field sensor, which can be used for industrial application. Actually, what you see in the center is a LED, and on top of the LED is a diamond with highly doped nitrogen, and around are photodiodes to detect the light, and this already is in use in a magnetic scale. Okay, in the superconducting field, we spent a lot of effort to develop in packaging technologies. This is one example where you have a 5 by 5 millimeter chip and 4 flip chip connected cryotrons on top. And this is one of the assembly approaches we also use for the qubit integration. We collaborate with IPHD in Jena, also in Germany. It's very close to Erfurt. They are producing aluminum-based qubits, and then we connect them to the AQFP circuits, which I will tell you in more detail right now. So the motivation is very simple, and it's basically based on the energy dissipation in computing, but we don't plan to build a computing system with the AQFP. We plan to build interface circuits. And then I will speak a little bit about energy dissipation in general and about the sensitivity, which is the main focus of this talk, because the question is, how sensitive can I make the comparator to get in contact with some very weak or very low energy component, and then I will conclude my talk. So I think I don't have to go in detail, but big data centers based on semiconductors, they have not only a big footprint, they also have a large demand for electrical power, and the idea of using more efficient computing systems is just to find some electronics which have a better energy efficiency. And maybe 20 years ago, the speed was most interesting for people, so clock frequencies were increasing, how many operations per second, and people were counting flops and gigaflops and so on. And today, most attractive or most interesting is this number, so the bit energy of 1 bit operation. And in this case, I have normalized it to the Josephson coupling energy because I'm interested in comparing different Josephson circuits. But in this second number, this is also very important. That's the energy delay product. It's not only important to have a low energy electronics, but also a certain speed is required. Maybe you don't need the fastest electronics, but the right product is important. So I put here one number up for CMOS. Of course, it makes no sense to give this normalization, but I have a typical clock frequency of 4 gigahertz and then some energy delay product in this order. And then I think RSFQ is well known, invented many years ago. It can run quite fast, but there's also a certain energy dissipation. And then later people came up with some more energy efficient approaches using Josephson junction as a digital switching element. And the one under investigation in our work is also not new. In the 80s, Professor Goto from Japan started to investigate the QFP, the quantum flux parametron. At that time, it was driven in a non-adiabatic mode, but later people found a way to change the circuit parameters. You can drive it adiabatically. What does it mean? It means that your current phase relation has no hysteresis anymore. You use a strongly nonlinear current phase relation, but there's no jump. So the phase of the Josephson junction always follows the excitation current. And if you don't drive it too fast, then it can directly follow it. So the energy dissipation is very low. So to get the best number in this comparison, and you see how far you also from the quantum limit. Okay, so now I switch first to the classical Josephson electronics, where you have the Josephson comparator as the most sensitive element to detect an incoming current. Basically, it's based on two Josephson junctions on top of each other, and you have an input signal, and the two junctions are part of a superconducting loop. So J1 is the driver, and it creates for every clock cycle, which is indicated here, for every clock cycle, it creates a single flux quantum, which is first stored in this loop, but the loop is too small, so the inductance is too small to store it. It creates a screening current, which is larger than the critical current, so eventually it forces the stack of the two junctions to switch. But the question is, which junction switches, J2 or J3, and this depends on the input current. So either J2 or J3 reproduces the clock pulse, and then if it was J3, you get also an output later. If J2 switches, you basically lose the clock pulse, and there's no information. And the practical circuit looks like this. You have here Josephson junctions. That's the clock driver, the pair in the comparator, and this is the output. You design it in a way that your threshold for the input current is around 0. This is not trivial. So if you make the two junctions equal, then you still have a large offset. You need to take into account that the lower junction has a load, and this is just engineering work. So electrical engineer optimize all the circuit parameter. This is just to give you an example, and it's the same circuit. And then later you investigate the sensitivity by scanning over different input currents. So the x-axis is the input current provided in this case from the bottom, and the y-axis is the probability of an output pulse. So in this example we applied 10,000 clock pulses and we counted the number of ones. If your input current is, for instance, minus 10 microamp, you get 0 output pulses. If it's plus 10, you get always an output pulse, so probability is 1. And then you have an error function in between. And you can see one important parameter here. This is the bias current of the two junctions, so IB1. And depending on the bias current, you see a different gray zone or different sensitivity. So this is one way to tune it, but the question is, so I put here 3 numbers, so is it getting, let's say, infinite better, or is there a limit? And we investigated this with such a circuit. This is the same comparator. It's surrounded by Josephson transmission lines to decouple it from the interface circuit, and we have a clock generator and output, and this is how experimental data looks like. Again, in this picture, you see a lot of different transition curves for different bias currents. In this case, I put the bias voltage, but that's the voltage which is turned into a bias current. And if you plot the gray zone versus this supply, then you see that you find a minimum point. So there is an optimal operation condition in terms of sensitivity. And for this circuit operating at liquid helium temperature, you reach something like 2.5 microamp. And this is giving you a lot of limitations for the best sensitivity you can obtain in ADCs or in other circuit elements. And it's also a limitation how you can connect to other elements. So we investigated, beside this current, other influence factors. One other factor is the clock frequency. And you can see it also depends on the clock frequency. So this is the real minimum. At very low frequencies, you can reach something like 2 microamp. But if your frequency goes up, then also this minimum point goes up. And if you reach something like 10 gigahertz, then already 5 microamp is a good number. So it's also a function of frequency. And last but not least, in digital circuits, one of the issues is timing jitter and delay. And you can simulate it, but you can also measure that the timing jitter and the delay of the comparator having a strong dependency on the input signal. And this is a problem, but it's very easy to understand. If your input current is far from the threshold, if it's really very low or very high, it's very easy for the comparator to make the decision. It's very quick, and it obtains the right result. But if your input current is around the threshold, so very close to 50%, it's much harder for the comparator to make the decision, and it takes longer. So you see an increase in the decision delay, but you also see an increase in the uncertainty. So it takes longer, but it's getting also more difficult. So this is also a problem in clocked systems, because you see here a big range. So it's like from 20 picosecond, it's going almost to 300 picosecond. And it's a little bit comparable if you're thinking about a two-dimensional hill and you're having a ball and you roll it to the hill. So if you go very left or very right, then it's very fast and it goes to the right decision. But if you almost hit the center, it takes the longest time. Eventually, if you go left or right. Same here in this circuit. So now I switched. This was the analysis of the Josephson comparators. Has been done many years ago. You can find all this. So all the key parameters are known. Recently, we started with our investigation of the ADIABATIC quantum flux parametron, and I will also analyze the sensitivity of this. So briefly, I want to explain the circuit. The AQFP consists of 2 Josephson junctions. They are in one superconducting loop, but in the center is a second inductor, and it separates the loop in 2 sides. I told you before that the current phase relation in this whole circuit does not allow a real switching. So it's always, let's say, following, the phase is always following the current. And you have an excitation line. This excitation line is driven by a sine wave, and you generate extra current in this loop. And in the transition point, the junction have to make a decision. You can understand this, that the current maybe goes clockwise, and it starts a current in J2 and in J1, opposite direction, but they both moving towards their critical current, and one of the junction is basically winning the race, and it changes and subpoint very quickly the phase, and then all the junction takes over this phase. And this creates a redistribution of the current to the center inductor, and then the loop is again in a stable operation point. You can also look at the potential energy. If there's no excitation current, then you have just one minimum point. And if you increase the excitation current, you generate 2 stable states. And for every clock cycle, the circuit makes a decision. So I just want to give some typical circuit parameters. In the experiments here, we analyzed AQFPs with critical currents of 50 microamp. This is the typical design value for circuits operating at 4 Kelvin. For our qubit control circuit, we aim lower critical currents, so 10 to 20 microamp, but they show already a little, let's say, bit error rate at 4 Kelvin. So it's a trade-off. But the other important question is about the sensitivity of this circuit. So I like to show you one experimental proof that the bit energy is really low. This is a nice experiment where the AQFP is connected to a network analyzer, and then you basically increase the excitation power, and you look how much of the power is taken from your system, and at some particular point you get a jump here. And if you calculate this backwards, then you get a proof that your switching energy is 10 zeta joule for 5 gigahertz excitation. And this is a very good agreement with the theory, and this is one of the things I like about the Josephson circuits, that the Josephson junction itself is easy to describe by mathematical equations. It's not like the transistors where we have very complex models with a lot of parameters you have to fit somehow, and they are not physical. So here it's in very good agreement, and we can also design quite complex circuits. One of the advantages is that the whole circuit always repeats the same fundamental cell. It's the AQFP cell I showed you before. You don't have to optimize and generate many, many different cells. It's basically an ensemble of many thousand of the same cells, and just the wiring depends what the circuit is doing. This is an example for a 16-word register file, which is part of a simple microprocessor we have designed and tested in Yokohama. I don't want to go into the details because I want to investigate the fundamental cell. This is again showing you the circuit diagram and the layout. What you see is that the actual squid with the two junction is very small. This is the excitation line, J1, J2, and this is already the loop. And the physical large part is the transformer, because you need an output transformer at the output. This is one of the reasons the scaling is limited for the circuit. You have a cell size of about 30 by 30 micrometer due to this transformer here. This is how typical let's say signals look like. That's simulation, because I show also phase signals, and this is an excitation current. The typical excitation is about 1 to 2 milliamp, and you have currents in the two junction in the range below 100 microamp, because you have 2 times 50 microamp junctions. And depending on the input signal, you can see where it switches. It's switched either in the one direction or in the opposite direction. The simulation also includes noise, but you see here obviously the sensitivity is good enough to overcome the noise. And these are the two phase values of the two junctions. So from the phase, it's very easy to distinguish which junction switches. But you also see here, this is all a transient change. There's no jump in the system. To measure the sensitivity, you do the same thing. You operate this with maybe 10,000 clock cycles. You change the input current and you sweep. And this is again such a measurement as I have shown you before. The input current on the x-axis and the probability of switching on the y-axis. And then you can fit the data. What was very interesting for us to see that it's in very good agreement with the error function. And why I was particularly looking at this, if you carefully look at the circuit here, you will find the Josephson junction have no external resistors, so they have no damping resistor. It's not necessary for the AQFP because your junction never switches, so it just follows, and the loop is so small that it's a very strong damping due to the inductor actually. So it has no free running of the phase. And then the question is, what is the origin of this gray zone or of the noise? And you want to make sure it's pure Gaussian noise and not something else. That's why I plotted here the difference from the error junction fit, which is also very small. So this is 0.4%. And this is just because of the statistics. If I put more numbers, it even gets better. So it's a very good agreement, but most important is now the number, what is the gray zone, and then we investigated this for different excitation signals. So the red curve is the gray zone, and most important dependence is on the rising edge of the excitation current. So if your excitation is very high frequency, then unfortunately also your gray zone gets large and you have this dependency. So for instance, for 1 megahertz excitation, you have something like 0.45 microamp. And at some point here it saturates at the lowest value, it's just below 0.4 microamp. For 4 Kelvin, that's the lowest value we could measure. And for all frequencies which are faster when here, it increases even. And you can also see a small threshold shift. This is the threshold here. It should be 0. Due to some imbalance, it wasn't 0, but it's also increasing a little bit. So the dependency on the excitation is normal. You can easily understand it from the bandwidth of the noise you allow. Because if you are operating at very high frequencies, you have a much higher bandwidth of noise coming into it. And the difficulty is to explain this saturation here. But we are currently investigating different temperatures to understand what is the influence of temperature to this. And this is an extension of the previous data by simulation. And we went to much higher frequencies and want to see what happens then. So at, for instance, 1 gigahertz, we are already at about 2 microamp grayzone. So this is very similar to the RSFQ circuits. So it's not really giving me significant better performance than the SFQ circuits. But if I go to something like a megahertz, then I can have at least a factor of 5 better sensitivity in comparison to the SFQ circuits. And lower frequencies is actually attractive because the AQFP power dissipation is a function of frequency. So if I operate it slower, I also get less and less dissipations. And of course, we investigated also all other parameters, most important parameter I showed you before. But for instance, the excitation amplitude has no influence. That's very interesting. So the excitation slope has a strong influence, but for the amplitude, threshold and sensitivity are independent. This is very good and is very different to the Josephson comparator. And now you can do some estimations. What is the maximum input signal you need? And here are some data points. And this is the input current you apply. And we assume an 0.4 microamp sensitivity. And then with this input currents, you get a certain probability for switching errors. If you want to build a very stable digital circuit, you're aiming for something like 10 to the minus 15. So then you see here you need input currents of about 5 microamp. And this is one of the reasons we're using AQFPs with lowest critical current of 10 microamp for our control circuits, because we want finally to come into a very classical stable regime. Maybe there are a lot of other influence factors. It will be hard to prove that we are here, but at least from the, let's say, first principles, we don't want to violate this. And I want also to give you a brief explanation why the Josephson comparator is about a factor of 5 worse than the AQFP comparator. This picture shows you a simulation of the Josephson phase for the 2 junctions of the comparator. And this is all around 0. So if I take the 2 junctions and allow them with some thermal noise to fluctuate, I get a distribution. And you can also describe this distribution. And there's a paper from 2012 which gives the explanation how to describe it. But you can also see that there's a certain shape which supports this direction. So if phase of junction 1 increases, phase of junction 2 likes to increase in the same way. This is due to the loop configuration in the Josephson comparator. In the AQFP, it's very different because your loop is much, much smaller, and you have another mode that one junction is driven in a positive way, the other junction is driven in a negative way. And you see here that it's not possible or not very likely that one junction increases the phase and the other one does the same. And this is actually the direction of the input current. And this is more clear in this picture here, that this is again the 2 structures, and I have a certain distribution coming from the thermal noise. And then the question is, what is the influence or the impact of a clock pulse, and what is the impact of the signal? And it's very important to see that the signal here belongs to the very narrow distribution. So this makes the AQFP comparator more sensitive when the Josephson comparator at the same temperature. And I don't want to give you some formulas, but you can also calculate this. But first we want to get more experimental data to compare this theoretical approach to the measured data. And this is some example for what you can do at low temperatures. So our circuits now are tested at 4 Kelvin with 50 microamp junctions. If you assume a very complex circuit with 100,000 gates at 5 gigahertz, you get a total power dissipation of 5 microwatt. This is still extremely low, but it's also a very complex circuit. So let's assume we want to go down to 300 millikelvin, and we are using much smaller critical currents, in principle 4 microamp as possible, and still a complex circuit with 10,000. Then we lower the frequency to 100 megahertz. Dissipation is a function of linear function of frequency. We end up with something like 0.5 nanowatt. And this is still possible at this temperature. So we think we have a good potential to come close to qubit circuits. And right now we're doing this flip chip bonding with qubits from IPHD. But we don't connect them at the moment. We just keep both parts independent and want to see that we can run both at the same time. And the next step will be, of course, an electrical or magnetic coupling of both to use this at the interface electronics. So I'm at the end of my presentation. I'd like to summarize that we have measured the minimum gray zone of the AQFP circuit at liquid helium temperature to be around 0.4 microamp. And the good thing is it's not influenced by excitation bias. And also, I haven't shown you the experimental data, but also some flux bias is not changing the sensitivity or the threshold. This is good because we may have some flux bias near to the qubits, so therefore we want to know this. The experimental data is in very good agreement to all the theoretical formulas, and we have investigated the dependency on the slope and have a good understanding of the mechanism, so we can also optimize the circuit. Everything operates extremely robust with 50 microamp junction, and with 20 microamp junction I can tell you that we can also get good results at 4 Kelvin, but we have, from the theory, one switching error in around maybe 10 to the 9 clock cycles. Experimentally, we have not investigated so much data, so we haven't seen it in experiments. So the 20 microamp circuits work stable, and we did this extrapolation. So I'm at the end of my presentation. Thank you very much.
Thank you for a nice presentation, and right now time for questions.
Thank you, Thomas. Can you all go 2 slides back? There was a table, yeah, here. Is this 100 megahertz a limit for low temperatures, or it's a by design?
No, it's not a limit. It's particular design for our setup, but in principle you may even consider lower frequencies. It depends what you want to do. If you, for instance, want to upload flux bias parameters for a lot of circuits, then you may do it just once, even with a megahertz or so, and then it's silent. But of course, if you want to have a continuous readout, then you have a certain repetition rate here. But you can also put here 5 gigahertz, then you get a higher dissipation. Yeah. So it's a trade-off.
Okay. And for the 4 Kelvin, 5 gigahertz is about the limit.
Yes.
What is the fundamental reason for this?
It's very simple, because it depends on your critical current density, and you have a maximum digital speed, comes from the plasma frequency, and you need to be about a factor of 10 below. It's a rough estimation. So this is based on the 10 kiloamp per square centimeter process from ACE in Japan, and this allows you an adiabatic operation of 5 gigahertz. If you would have a higher JC, you could go a little bit higher, but it's still in this range.
thank you.
Actually, we don't aim for frequencies like this because we don't want to come close to qubit frequencies.
Okay.
Other questions?
I was going to ask you about Mach-Gamber parameters for your junctions in the balance comparator and in AQ comparator.
So in early designs, we used the Mach-Gamber parameter of 1. But later, we completely removed the resistors. So they have a Mach-Gamber parameter of maybe 20, 50, we don't know exactly. The junction itself is not externally damped. But the loop configuration here provides a very strong, you can see it as a damping. The phase cannot make jumps.
But using off-tunnel junctions with high Mach-Gamber parameter sometimes.
That's true, you can extract it, but we don't even have junctions to measure it on the chip. I can check data from Japan, what they have, but in all the circuit, they are always in these loop configurations, so they are basically shorted by an inductor. So this loop is about 2 pico.
Another questions?
I'm wondering, what is the readout time, your target readout time, and what is the ring down time, which would, of course, limit the repetition cycle?
So this goes into the direction why we choose the 100 megahertz. So we think we have ring downtime of about a nanosecond. And we want to make sure, so we choose 10 times this number to make sure everything is really in equilibrium when we start. And the readout is just depending on this slope, because you have a certain fraction of the slope where the comparator is sensitive. So if you think about 100 megahertz, then this is also, again, roughly a nanosecond is the readout time.
Okay. Another questions? Okay, I have a question. Are there some works for not a single adiabatic comparator, but a network of comparators? If this is there, what is about interaction between basic elements? Or it's just independent elements?
It's a good question. I don't know about, let's say, scientific investigation of this, but one of the features in the complex circuit is that you have a lot of AQFPs connected to one excitation line, and they're all making a decision at the same moment. And we observe that if they're all in a digital mode, it means they get all a very well-defined positive or negative input. Then there's no problem. But if you drive more than one with an excitation line in this, let's say, analog mode, where you have a very sensitive input signal around 0, then you see a crosstalk between the comparators by the excitation line. So you have to take this into account. You can clock complex circuits with one excitation line, but if you have more than one comparator, you cannot easily connect this.
Thank you. Okay, if
Can you comment on the closed cycle refrigerator operating for AQFP circuits compared to SFQ? Is it same difficulty, or it's more sensitive to closed cycle refrigerator noise, or?
It's very robust,
Robust?
To the clock. I mean, you have an AC clock, so you feed a sine wave to the cryostat. So you need at least one, maybe 2 excitation lines at 100 megahertz or something like this. But you don't have a propagation of jitter, so every time it's synchronized by this external clock, and the amplitude of the clock is not increasing by the circuit complexity, so it's fixed.
Okay.
I think that's all, and thank again for this presentation, and this is diploma. Okay.
Thank you.
Okay, and we go to another last talk of this first part of. Speaker is not here. Ah, okay. Okay. No online presentation also.